2.1 and 2.2 Lesson 2, Numerical, Graphical, and Algebraic Approaches to the Definition of Limit. Our objectives for today's lesson are: you will know two ways in which the limit of f of x as x approaches c may fail to exist. So yesterday we began by thinking about what we mean by a limit, what a limit is, and what a limit is not. Today we're going to look at two examples in which the limit of the function as x approaches c will fail to exist. And then we'll take a look at objective 2. Given f of x and the limit of f of x as x approaches c is equal to L, you'll be able to determine how close the input values x must be to c so that the output values will be within a specified distance from the limit L. So vocabulary for today is limit. As we look at objective 1, we will talk about what we mean by a two-sided limit, which is what we considered yesterday, and what is a one-sided limit. And then as we look at objective 2, we will look at the Greek letters epsilon and delta and how they're used to help us be more precise in our discussion of what a limit is. So now we will begin by looking at objective 1. You will know two ways in which the limit of f of x as x approaches c may fail to exist. So here we will look at numbers 1 and 2, and looking at these two problems will help us to understand the two ways in which the limit of f of x as x approaches c may fail to exist. So let's look at number 1. So we have the limit of f of x as x approaches c. So when you look at the graph for the function f for number 1, on the x-axis we have c here. So how do you understand what this is stating? It's stating that the input values, or the x values for the function, are approaching c. So you can have input values approach c from the left of c or from the right of c. And when that's happening, are the output values or the y values of the function approaching a single number? The answer is no. If the input values are approaching c from the left, the output values are approaching 1. But if the input values are approaching c from the right, the output values are approaching 2. Because the output values are not approaching a single number, we say the limit does not exist. So that is one way in which a limit may fail to exist. As the input values approach c from both sides of c, the output values are not approaching a single number. Let's take a look at number 2 here. Here's another way in which the limit of the function as x approaches c may fail to exist. So x is approaching c from the left of c and from the right of c, and the question that you have is, when the input values are approaching c from either side, are the output values approaching a single number? And we don't have that happening here because the output values continue to increase without bound as x approaches c from the left of c, and the output values also continue to increase without bound as x approaches c from the right of c. And because the output values are not approaching a single number, we say this limit does not exist. The output values are going to infinity, and that is one way in which a limit fails to exist. Later, you could indicate that the limit does not exist by specifying the manner in which it fails to exist, namely that the output values are going to infinity. But that's a way of specifying the manner in which the limit fails to exist for this particular problem. Now we will go back to number 1, and we'd like to talk about one-sided limits. So it is true that the two-sided limit does not exist. As x approaches c from either side of c, the output values are not approaching a particular number or a single output value. That's not happening. However, you can do this. You can think about what's going on as x is approaching c only from one side of c. And if you use this symbol, a superscript of a negative sign, that means x is approaching c from values that are less than c. And when that's happening, you can see that the output values of the function are approaching the number 1. So you can say the one-sided limit of f of x as x approaches c from the left is equal to 1. And you can do the same thing about the one-sided limit of f of x as x approaches c from the right side of c. And when you have that superscript of a positive sign or a plus sign, that means the input values are approaching c from the right of c. And you can see from the graph that when the input values are approaching c from the right of c, the output values are approaching the number 2. So here, the one-sided limit is equal to 2. And in fact, it is a requirement for the two-sided limit to exist that the one-sided limits exist and are equal to each other. And what we have here is that the one-sided limits, they exist, but they're not equal to each other. And that is why the two-sided limit does not exist. So we just completed objective 1. You now know two ways in which the limit of f of x as x approaches c may fail to exist. Let's take a look at objective 2. Given f of x and the limit of f of x as x approaches c is equal to L, you will be able to determine how close the input values have to be to c so that the output values will be within a specified distance from L. And that specified distance from L is signified by epsilon, and you will be able to determine how close the input values have to be to c, and that distance is specified by delta. So that's where epsilon and delta come in. So let's take a look at what instructions for the problems that we want to look at would be like. So we will be actually having a graph that we will be looking at. For the point marked on the graph, use proper limit notation to write the limit of f of x. Proper limit notation means you write the limit of f of x as x approaches c is equal to whatever it's equal to. That's what proper limit notation means. For the given value of epsilon, so we talked about what epsilon is, and when we look at our examples, there will be a given value for epsilon. It tells you how far the output values can be from whatever the limit is. Estimate to 1 decimal place the largest possible value of delta, and we talked about what delta is. It tells you how close the input values have to be to c. So for the given value of epsilon, estimate to 1 decimal place the largest possible value of delta that you can use to keep the output values within epsilon units of the marked point, which would be the limit, whenever the input values are within delta units of the value shown. So you will understand what that is when we look at our example. We will actually look at 2 examples. So for the 2 examples that we look at today, we're going to look at the graph, which I have done on Desmos, and we're going to find the limit of the function as x approaches the given value and write that limit using proper limit notation. And we're going to find that limit graphically, as we did yesterday. And then we'll look at part C. Find the maximum value of delta, which tells you how close the input values have to be to C. Find the maximum value of delta that can be used for a given value of epsilon at the point. And epsilon tells you the furthest you can be from the limit. The furthest the output values of the function can be from the limit. We'll look at part D tomorrow. So we begin by looking at our first example, which is number 19. our function for number 19 is f of x is equal to 5 minus 2 times sine of x minus 3, which I have graphed using Desmos, and you can see the sine wave there. So that's part A. Plot the graph on your grapher. How does the graph relate to problems 13 to 18? Well, this is the part that we want to concentrate on. And then for part B, it says find the limit of the function as x approaches the given value. The given value is 3. So we want to find the limit of f of x, and you can see that I'm writing the limit using proper mathematical notation. You should do that for all problems. The limit of f of x as x approaches 3 is equal to, and let's go ahead and find that limit by using the graph that we're looking at. Find the limit of the function as x approaches the given value. And you can see that the given value for x is 3. So as x approaches 3, from the left of 3 and from the right of 3, the output values from the function are approaching what number? Well, if you look at the graph of f of x, you can see that as the input values approach 3 from the left, and as the input values approach 3 from the right, the output values are approaching 5. So the limit of f of x as x approaches 3 is 5. Now we want to take a look at part C. Find the maximum value of delta that can be used for the given value of epsilon at that point. And if you look at the problem for number 19, the given value of epsilon is 0.5. And as I had told you before, epsilon tells you how far the output values for the function can be from the limit. So the limit is 5. So when epsilon is 0.5, we're basically saying, let's look at output values from the function that are either 5 plus epsilon or 5 minus epsilon. So the limit is 5. Epsilon is 0.5. So you can have output values from the function f that are either 0.5 more than 5 or 0.5 less than 5. So your output values can range between 4.5 and 5.5 within a half unit of the limit. So that's what we're talking about in part C. Find the maximum value of delta, so now we're going to talk about that. But find the maximum value of delta that can be used for the given value of epsilon at the point. And epsilon tells you how far the output values of the function f can be from the limit. So what is it that we want to do in part C? Find the maximum value of delta that can be used for the given value of epsilon at the point. So delta is talking about how close the input values have to be to 3. So we're taking the limit of f of x as x approaches 3. So we want to know how close do the input values have to be to 3, and that's what delta is. Find the maximum value of delta, which will tell us how close the input values have to be to 3, so that the output values will be within a half unit of the limit. So to do that, we're going to look at these two. We look at the graph of f, which is the sine curve shown in red, and we look at what the limit is. As I wrote earlier, the limit of f of x as x approaches 3 is equal to 5. And the given value of epsilon in our problem is 0.5. So we have the limit plus epsilon, which would be 5 plus 0.5. And I graphed the horizontal line y is equal to 5.5, which is right here. I'm tracing it in black now. And then I graphed the horizontal line y is equal to the limit minus epsilon, 5 minus 0.5, which is y is equal to 4.5. And I'm going to trace that in gold right now. So we're looking at this window for what the output values of the function can be. The output values of the function can be within a half unit of the limit. So the output values can be within 4.5 to 5.5. So now the question is, for that to happen, how close do the input values have to be to 3? That's the question. And you can see from the graph, and I'll show you with these two vertical lines. If you look at these two vertical lines, basically when the input values for the function are within the interval from 2.747 to 3.253, and maybe I want to round up here to 2.75 just to be sure. So I have 2.75, and then here maybe I want to round down to 3.25. So basically when the input values are within the interval 2.75 to 3.25, I can be sure that the output values will be within the interval from 4.5 to 5.5. And that is what part C is asking us. Find the maximum value of delta that can be used for the given value of epsilon at the point. So I'm going to say delta is going to be approximately, how far is 2.75 from 3? It's 0.25 units away from 3. So when you have x values that are within 0.25 units from 3, the y values will be within 0.5 units from the limit 5. And that's basically what this problem is about. So we just looked at one example for objective 2. Given f of x and the limit of f of x as x approaches c is equal to L, you'll be able to determine how close x must be to c. In the problem that we just looked at, we said x must be within 0.25 units of c, which in our problem was 3, so that f of x will be within a specified distance from L. So that in the problem that we looked at, the output values will be within 0.5 units of the limit. And that 0.5 was the epsilon value, and the delta value that we found for how close x has to be to 3, that was 0.25, and that was the delta value. So now we'll look at a second example for the same objective, same instructions. So now we take a look at number 20, and the first thing that we want to do is plot the graph. The function that we have is f of x is equal to x minus 2 cubed plus 3, and here you see the graph of the function f. The second thing that we want to do is find the limit of the function as x approaches the given value. The given value is x is equal to 2, so we want to use proper limit notation. We write the limit of f of x as x approaches 2 is equal to, and we will find this limit graphically. So as you can see from our graph here, here is 2 on the x-axis. So as the input values approach 2 from the left and from the right, the output values are approaching what number? So let's go ahead and take a look at our graph. So as the input values approach 2 from the left, the output values are approaching 3. As the input values approach 2 from the right, the output values are also approaching 3. So the limit of f of x as x approaches 2 from either side is 3. So that's part B. And part C says, find the maximum value of delta that can be used for the given value of epsilon at the point. And if you look at number 20, the given value of epsilon is 0.5. So what does that mean? Again, that means you're going to let the output values of the function f vary from the limit by as much as epsilon equal to 0.5. So the output values for the function that you are considering can be the limit plus epsilon or the limit minus epsilon. So they can be between 2.5 and 3.5. So you're looking at output values from the function that are in this range, from 2.5 to 3.5. So the question is, for that to happen, what are the possible input values? And how close do they have to be to 2? And that is called delta. And let's look at part C. Find the maximum value of delta that can be used for the given value of epsilon at the point. So how close do the input values have to be to 2 so that the output values will be within a half unit of the limit 3? To answer that question, I went ahead and graphed y is equal to 3 plus 0.5, or y is equal to 3.5, whose graph I'm tracing in black here. And then I went ahead and graphed y is equal to 3 minus 0.5, or y is equal to 2.5, whose graph I'm tracing in blue now. So this is the range of output values that we're considering, from 2.5 to 3.5. They are within a half unit of the limit. So to find the maximum value of delta that can be used for the given value of epsilon, this is what I have to do. I'm going to think, okay, so I'm going to have my input values to be within delta units from C, and C is of course 2. So I'll have 2 minus delta here, and I'll have 2 plus delta here. Just like for y, what did I have? Where did 2.5 come from? It came from the limit, which was 3 minus epsilon, and where did 3.5 come from? It came from the limit, which was 3 plus epsilon. So more generally, what we're doing is, whatever the limit is, you have the limit minus epsilon, and you have the limit plus epsilon for the range of output values that we're considering. And whatever C is, you have C minus delta and C plus delta for the range of input values that would give us output values from this range. So how do you figure out what delta should be for this particular problem? And for this particular problem, C is, of course, 2, and L for this particular problem is 3. So how do you figure out what delta should be? Well, if you look at these two vertical lines that I'm showing in green here, what you can see is that when the input values are between 1.206 and 2.794, the output values will be within the range from 2.5 to 3.5, or within a half unit of the limit, within epsilon of the limit. So what does delta need to be? So you can round up a little bit here, so you can make this 1.21, and you can round down a little bit here, make this 2.79. So basically, how do you get 2.79? You have to add 0.79 to 2. So that's going to be your delta value. Your delta value will be 0.79. And if you do 2 minus 0.79, again, your delta value is 0.79. 2 minus 0.79 will give you 1.21. So that's going to be 2 minus 0.79 will give you 1.21. 2 plus 0.79 will give you 2.79. So when the input values are within 79 hundredths of C, the output values will be within 5/10 of the limit. And the main idea that you want to get from this lesson is that the smaller you make epsilon, the smaller delta would have to be to satisfy the requirement that the output values have to be within epsilon units of the limit. And if you can find a delta value for any epsilon, no matter how small, we say the limit of the function as x approaches c exists. And that's what we're going to look at tomorrow. So we just looked at our second example for objective 2. Given a function f of x and the limit of f of x as x approaches c is equal to L, you'll be able to determine how close x must be to c. And that distance is specified by delta, so that f of x will be within a specified distance epsilon from L.